Good afternoon, everybody. Lead telluride, cadmium telluride is experimentally and physically very rich heterosystem, which is investigated by me for several years, and I can say I know about it quite a lot, but it still surprises me. So today I decide to tell you a little bit more about it to give you some image of this. So I will start at the beginning from the optical properties of the lead telluride, cadmium telluride nanocomposite obtained by molecular beam epitaxy. In this area, I strongly collaborate with Professor Karczewski team, and then I introduce the ZT parameter and tell about thermoelectric properties of this nanocomposite and about the monocrystalline lead cadmium telluride solid solution bulk samples which were obtained by self-selecting vapor growth method. The main part of my talk will be novel, just patented method of obtaining bulk lead telluride cadmium telluride nanocomposite, which the method we developed together with Professor Michał's team and his company Pure Math Technologies, and with support from colleagues from MACTOP and other divisions. And finally, I will talk about an alternative method of obtaining composite based on lead telluride. I mean the extrusion method, which we were working on together with colleagues from Warsaw and from Krakow in the ThermoD project. So at the beginning, let's think how to obtain lead telluride, cadmium telluride nanocomposite by molecular beam epitaxy. It occurs to be very simple. We only need to anneal the multi-layer sample. In this case, in the case of this method, the formation, for example, the lead telluride quantum dot in cadmium telluride matrix is driven by difference in the crystal structure of both semiconductors. We know the lead telluride, it is narrow gap semiconductor which crystallizes in rock salt structure, while the cadmium telluride, it is zinc blende, it is wide gap semiconductor which crystallizes in zinc blende structure. Because of this difference, both semiconductors are in practice immiscible at temperature of around 300 degrees, which is the typical growth temperature. This method was originally presented by Hayes and collaborators from Professor Springhold's team, but I think that together with Professor Karczewski, we took this method on the higher level. What I mean? I mean that by proper control of growth parameters like initial thickness of layers, growth temperature, time and temperature of annealing, we can obtain the nanocomposite with very complicated internal morphology, which at first glance look completely chaotic, but at second glance, we start to see more regular structures similar to the resonant cavities, or with hexagonal symmetry, what will be better visible on the next slide. Anyway, our nanocomposite exhibits very strong, surprisingly narrow emission, if take into account the spreading of the sizes of the objects in our composite, which is always blue shifted of about 15 milli-electron volt as compared to the emission from bulk lead telluride, which is due to the quantum size effect. But the quantum size effect, it is not only what we can see in our structures. The hexagonal symmetry help us to understand the results of the experiment in which photoluminescence was excited and collected from the edge of the sample. This is some kind of microluminescence measurements because the total thickness of the sample is of about 1 micron. In the case of this sample, in such measurement, we observe the rather wide this time emission with clearly visible internal structure. This internal structure can be described by whispering gallery modes of resonator, of hexagonal resonator, which are present in our sample. It is clearly seen in this picture. Another interesting result we have obtained in measurement of excitation power dependency of photoluminescence. For example, for the sample which initial design shown here, we have observed the emission which appears for higher power excitation and which exhibit laser-like behavior. This emission we bound with enhancement of photoluminescence due to interaction with plasmons from the two-dimensional gas which is present at the interfaces between lead telluride and cadmium telluride. The presence of this the two-dimensional gas is expected due to band bending at the interfaces. To finish with optics, I cannot fail to mention about the photonic effects, which are expected to be very strong in the case of lead telluride, cadmium telluride heterosystem, because of big difference of refraction indexes for both material. You know that photonic structure, it is the structure with periodically changing refraction index in 1, 2, or in 3 directions, but the most important at the moment is that within the lead telluride, cadmium telluride heterosystem, using molecular beam epitaxy, we can obtain all 3 kinds of photonic structures. Here we have an example of the reflectivity spectra obtained for the simplest photonic structure. I mean the Bragg mirror. We see very nice stop band, which is obtained for the sample, which contain only 5 repetitions of lead telluride, cadmium telluride layers. So let me switch to the thermoelectricity. Thermoelectric efficiency is described by dimensionless parameter, dimensional figure of merit parameter known as ZT, which is direct proportional to the Seebeck coefficient, electrical conductivity and temperature, and inversely proportional to the thermal conductivity. Of course, I'm sorry, of course, higher ZT is better. The increasing ZT looks like a simple task, but it is not true, because all these parameters are internally dependent. Nevertheless, we can try to increase the ZT parameter by preparation of low-dimensional structure, or by additional doping, or by increasing the temperature, or by introducing the other elements or other phases to the sample. But it seems to us that the best approximation to this problem is the preparation of the nanocomposite from known thermoelectrics as lead telluride is. And the question is how to prepare the nanocomposite from lead telluride using molecular beam epitaxy. It is always very simple task, because we need only invert the thickness ratio of the layers in the initial structure. Using this method, we can well control the size and distribution of cadmium telluride grains in our nanocomposite by proper choice of the initial thickness of the layers, as shown on this panel. For the samples with the smallest grains, we have observed increase of the Seebeck coefficient of about 13% as compared to the best bulk lead telluride samples, what is depicted by this black line. Of course, nanocomposite obtained by molecular beam epitaxy are excellent for the testing of new thermoelectric idea, and most probably can be used in the low power application, I mean the thermoelectric integrated circuits. But for high power application, we need the material which can conduct 5 or 6 ampere of electrical current and which can work at big gradient of temperature of about 200 degrees. So to this purpose, we need to have the bulk samples. To do it and to check the influence of the cadmium dopant on the thermoelectric properties of lead telluride, we use self-selecting vapor growth method, which is the method which was developed by Andrzej Szczerbakov in our team, and now the works are continued by Jędrzej Korczak. Nevertheless, using this method, we have obtained high-quality monocrystalline lead cadmium telluride bulk samples with cadmium content of about 11%. And for such samples, we have observed almost twofold advancement of thermal power as compared to pure PbTe and twofold decrease of thermal conductivity as compared, of course, to pure lead telluride. However, ZT parameter for such high cadmium content sample is strongly limited by damping of mobility due to alloy scattering of electrons in our sample, and moreover, we cannot compensate this effect by, for example, additional doping, by additional carrier concentration because of difficulties with doping if in the case of this method. So let me summarize a little bit. We have the molecular beam epitaxy method in which we can control well distribution and sizes of cadmium telluride grains. We can also dope this sample, but they have very small working value. We have the self-selecting vapor growth method. We can obtain with this method big sample with well-controlled cadmium content, but there's a problem with doping in this case. So the question is there the method which allow us to control all relevant for nanocomposite parameters? Yes, this method was just patented and is described in details in European Patent Bulletin. Let's say a few words about the methods. In this method, we deliberately use extremely low mutual solubility of both materials, and the method consists of few key steps. I mean, first step, the proper preparation of input material in the form of elemental lead, tellurium, and cadmium in the form of compound. These elements are mixed and put it into the quartz ampulla, sealed, and put it into the two-zone electrical oven. The next step, it is the dissolving of the material at temperature which is above the melting point of lead telluride, but below the melting point of cadmium telluride. It prevents the complete dissolution of cadmium telluride in our samples. After complete dissolution of the input material, the ampulla with this material is rocked with frequency of about half hertz over 15 minutes, and then the next key step is put it down and fast crystallization takes place. Using this method, we can obtain samples with cadmium content up to intentional cadmium content up to 10%, and we dope this sample with with iodine or with bismuth for N-type conductivity and conductivity, and with sodium for P-type, just by adding proper elements to the ampulla before the growth. But the question is what it means, really means the rocking of the ampulla. Let's see. This setup was designed and built on by the team of Professor Michalski, and we see very nice heated to the high temperature ampulla here, and the process is taken at high temperature, as I said, and the frequency can be changed if you want. This setup was designed for the other purpose, and it is also patented. So let's check results of our growth. Our samples were examined by XRD diffraction method, and we have found that all of our samples exhibit polycrystalline structure, what is the expected and needed from thermoelectrical point of view effect. We have also found that lattice parameter of our nanocomposite follows the changes on cadmium content observed for monocrystalline sample up to cadmium content of about 2%. For higher cadmium content, the lattice parameter decreases much slower, or remains unchanged. We have also checked the distribution of cadmium along the ingots, and we have found that it is quite uniform, but cadmium content taken from the X-ray measurements differs from that obtained for EDX analysis. Moreover, if you look more carefully of the X-ray data, we see that high index Bragg peaks exhibit asymmetry, which asymmetry increases with increasing cadmium content, and can be described properly if we take into account the presence of additional cadmium telluride phase in our samples. So we can conclude that in our samples, the cadmium telluride is present, especially for the samples with higher content, in the form of cadmium telluride precipitations. Let's check, is it proper conclusions. To check this, we use the CEM microscope, and we have found that for samples containing of about 2% cadmium content, there is no visible precipitation in our sample, what matches very well to the X-ray data. But for samples which contain of about 5 or 10% cadmium content, we see very nice uniformly distributed grains with the sizes of about 100 nanometer in the case of 5% sample, and with the sizes of about 300 nanometers in the case of 10% sample. If you look more carefully, we see also the sign of some self-selecting processes which are present in our sample. To check the composition of our grains, we use the X method, and we have found that they consist from cadmium telluride. So it means that our methods really work. All our samples, for our nanocomposite, we performed the basic electrical characterization, and we have found samples p-type conductivity and with n-type conductivity and with carrier concentration from 10 to 17 per cubic centimeter for the undoped sample, and with carrier concentration of about 10 to 19 per cubic centimeter for sample doped with all of these elements. So for the best, electrically best sample, we perform measurement of thermoelectric efficiency. I mean, we have measured the ZT parameter using Harman method, which is direct method, which need only measurements of AC and DC resistivity. And as a result, we have obtained that ZT parameter for our samples reaches value of about 0.7, 0.8 for all checked sample, what is a very good preliminary result if we take into account our previous theoretical predictions, which indicates that for samples with a little bit higher concentration, the ZT parameter may be much higher than 1. So I can conclude that this method works properly, and it is very promising for the preparation of the thermoelectric materials. And I hope that it will be used maybe in future for preparation of devices which we can buy at market. Okay. Now let me say a few words about our recent thermoelectric project. I mean the ThermoD project, which we were working on together with colleagues from a few institutions from Warsaw and from Krakow. The goal of the project was developing a technology for manufacturing a new type of thermoelectrics modules for the conversion of low parameter waste heat into electricity. The project was financed by National Center for Research and Development within the TechMat-Stratec project. The project was realized within the consortium, consists of a few institutions from Krakow, I mean the Krakow Institute of Technology, University of Science and Technology, Institute of Microelectronics and Photonics from Warsaw, and of course our institute, and with one private company, Helioenergia. The project manager was Professor Krzysztof Wojciechowski from University of Science and Technology from Krakow. Each institution had your own tasks, and the colleagues from Krakow institutions' task was preparation, design the thermoelectric module and simulating its electrical characteristics, and designing and construction of the extruder machine, which were the key element of the project. Our institution and Institute of Microelectronics and Photonics task was preparation of input materials. In our case, it was based on lead telluride, which was synthesized from elements with not high purity, and by fast Bridgman method, all of this to decrease the cost of the material. The colleagues from Institute of Microelectronics prepared the materials, input materials based on bismuth telluride and bismuth selenide compounds. The Helioenergia task was designing of electrical connections with nano-silver paste and with use instead of ceramic substrate, which are very expensive, the anodized aluminum. The main task of the project was, first of all, the designing of the thermoelectric module with power density of about 1 watts per square centimeter and reducing the cost of single module. Another task was optimization the parameters of extrusion process and geometry of extruder, which are shown of extruder matrix, which are shown here. It was expected that extrusion process may improve thermoelectric properties of the materials as compared to the materials obtained by commonly used methods as spark plasma sintering or growth obtained from monocrystals. So let's see on the results. Here we have a few examples of results of extrusion obtained for our lead telluride materials, and we see that proper choice of the extrusion parameter, like pressing force, matrix temperature, temperature before the channel and the temperature of the channel, and most important, the speed of the extrusion are critical to the final effects. Anyway, we found the proper conditions, and material which was obtained by extrusion method exhibit very, very promising thermoelectric properties with the T parameter reaching of about 0.7. However, the parameter for extrusion, unfortunately, were found at the end of the project. So the thermoelectric modules which were used for construction of demo thermoelectric generator were based on the bismuth compounds. Nevertheless, the obtained modules have very good maximal power with about 6 watts and very good power density of about 2.4 kilowatts per square meter, and demo thermoelectric generator which were working at temperature between 200 degrees and 25 degrees exhibit the total power of about 140 watts. So the result, the project was finished, I think, successfully, and our consortium have obtained the nomination from institution known as Intelligent Development Forum, have obtained the nomination for the award in the category of research team of the future. So let me summarize my talk. First of all, we propose a novel method just patented of obtaining bulk lead telluride, cadmium telluride with very controllable working volume, carrier concentration, distribution, and sizes of cadmium telluride grains inside. We have also developed within the project alternative method of obtaining such nanocomposite, which is expected to be very effective and cheaper than the method which are commonly used in factories. And finally, we should also remember that lead telluride, cadmium telluride heterostructure is not only application but also intrinsic physics. I mean, I mean, for example, photonic effects. Photonic effects was a key feature which was strongly exploited in my recent project concerning the detectivity of the lead-telluride cadmium telluride heterostructures. I hope I can speak about the results soon. Thank you for your attention.